VORAGO Technologies receive a lot of questions about the CubeSat Onboard Computer Reference Design Kit. This short video addresses the most frequently asked questions. What is the purpose of the board design? There are lots of options for engineers to choose an off-the-shelf CubeSat onboard computer that doesn't have radiation hardened components. We were encouraged to create an option for engineers that uses rad-hard ICs. The motivation was to provide a design that provides a longer mission life expectancy than typical non-rad hardened solutions and allows flight beyond LEO through radiation effects mitigation. Do you expect people to fly the board as it is? We expect so. We designed and built the board carefully using good quality materials and established industry standard practices. We wanted to keep the cost of the board as low as possible but still use radiation hardened ICs. We could spend more money on further component upgrades, testing and qualification, but we think that we've achieved a robust level and further price increases of the board would lead to diminishing returns. Has it flown already? Well, as of late February 2019, the board has not yet flown. At least one of our customers has plans to launch the board in a LEO mission later in 2019. What sort of testing and qualification has been done on the board? We built and tested the board to comply with best industry practices for industrial grade PCBs. The boards are manufactured and tested onshore in the USA. We have not yet performed any environmental or vibration testing on the board. NASA is planning on doing board level radiation testing on the RH-OBC-1 in 2019. We will make the radiation testing results public when they're available. Are all of the components flight-grade radiation-hardened ICs? The VORAGO microcontroller is a rad-hard VORAGO high-rel qual device based upon MIL standard 883, AEC Q100, JEDEC and radiation testing. We've used prototype-grade Cypress FRAM and flash, Intersil supervisors and LDOs, and a COBOM ADC. We used prototype grade to keep the price of the board as low as possible. Flight grade devices are typically 2x the price. We've also used an automotive grade Cypress FRAM, automotive grade CAN transceiver, and a commercial grade USB IC. The USB IC was never intended to be used in space. It's intended for code development and potentially data collection on the bench. The USB IC is not powered from the 5V supply from the CubeSat bus, so would not be a liability in a radiation environment. Are there any high reliability circuit design techniques used? Yes. Even though all of the key ICs are rad-hard, we still use a supervisor IC that is itself rad-hard that monitors supply voltages and has an independent watchdog function. The USB IC is not intended to be operated in flight and is disconnected when the board is not used on the bench. The automotive grade CAN transceiver is monitored externally using discrete components so that it can be reset if it is observed to be succumbing to radiation effects. The microcontroller also observes register contents of the CAN IC to ensure that it's operating to expectations. Why did you choose the Pumpkin CubeSat Kit Bus interface? There are lots of plug-and-play CubeSat components and boards available from Pumpkin Space Systems. We responded to requests for the creation of a rad-hard OBC that could be used with the other Pumpkin CubeSat Kit Bus components. We've tested the RH-OBC-1 with Pumpkin boards for compatibility. Is this a product for sale by VORAGO or is it a reference design? It's actually both. It started off as a reference design to make it easy for designers to use the VORAGO VA10820 microcontroller, and then we were asked by customers to build a few units to sell to them. We understand that one size doesn't fit all, so we expect that a lot of folks will want to make modifications to the basic design. So we supply all the relevant files to make it as easy as possible for designers to accomplish those modifications. These modifications are typically things like different power supplies, leading to a change in the voltage regulator on the board, or different interfaces required, leading to changes in the type of transceiver circuits that are connected to the microcontroller.